Now today let us start transmission and distribution class. Second module, we are talking about transmission line parameters. The electrical power generated in the generating station is actually transmitted with the help of transmission line, which are normally overhead. The parameters associated with these transmission lines are inductance, capacitance, resistance, and conductance. The performance actually of the transmission line is dependent on all these parameters. As everyone knows, these parameters are uniformly distributed along the length of the transmission line. The efficiency and voltage regulation, whether it is good or poor, it will be determined from these constants. For good electrical design of transmission line, a sound knowledge about all these parameters are very much essential. That's why today we are discussing as a first topic transmission line constants. Conductance between two conductors or between conductors and the ground accounts for the leakage current at the insulator of overhead lines and through the insulation of cables. The leakage at insulators of overhead lines is negligible. The conductance of an overhead line is also assumed to be zero. So let us begin with a concept called transmission line constants. The transmission lines, you know that they are the circuits with the distributed constants such as resistance, inductance, capacitance, conductance. It is distributed all along the length of the transmission line. You can see here as shown in the diagram. These constants are not concentrated at one particular point. Got it? Their values are normally expressed as per kilometer length of the line. Please understand. Consider this circuit. The analysis of the circuit can be made by lumping the parameters. Okay, that I have shown in the second diagram. You can see the next diagram. Now, the analysis of circuit becomes very easy by lumping the parameter as the same current is passing through the each element of the resistance and inductance. Now, similarly, the circuits shown in the figure here, both A and B, you can see here the diagrams. Okay, they are nothing but equivalent as the same voltage is applied across each conductance and capacitance. But if the elements are distributed as shown in here, as shown in this diagram, then the elements cannot be lumped as the same current is not flowing through the series element and the voltage across the different elements changes from one section to other. Keep that in your mind. Consider the equivalent circuit. Okay, here this actually speaks about the conductors. Now you understood about how the circuits equivalent circuit, I mean how the same voltage is applied across each conductance and capacitance, and how the circuit, I mean all the elements are lumped with which are connected in series and which elements are lumped, and how exactly the current distribution happens. Everything you understood. Now we are moving on to the next concept, that is resistance of a transmission line. Here, the resistance of a transmission line is very important parameter as it is the main cause of power loss in transmission line that everyone knows. You know that. If you want, you can define that. It is an opposition offered by the transmission line conductors to the flow of current. The resistance of the line is uniformly distributed. We know that along its whole length, how much the transmission line is, that much the whole it's uniformly distributed all over the length of the transmission line that everyone knows. But the performance of the line can be conveniently analyzed by considering the distributed resistance as lumped one. We know that always we do that, right? We don't write, we'll write the symbolic representation of this is, we know that already. It's actually considered as lumped instead of distributed. The effective resistance of a conductor is given by R is equal to P by I square. R is equal to rho L by A When it is given, when the distribution of current in a conductor is uniform, then the effective resistance is equal to DC resistance of the conductor. Got it? This direct resistance is given by rho L by A. I have written here. You can see in this slide where rho is the resistivity of conductor, L is the length of the conductor, A is the cross-sectional area of conductor. This DC resistance computed from the above equation of the standard conductors. It's actually greater as spiraling of the strands make them longer than the conductor itself. This increases in resistance is taken as 1% for 3 strand conductors and 2% for concentrically stranded conductors. Temperature is also one of the factor which will change the DC resistance of the metallic conductor, because you know that coefficient thermal expansion, right? Now its variation with resistance will be there always. From this we can write R2 is equal to R2 and R1. If I say those are the resistances of the conductor at temperature T1 and T2 in degree centigrades, and if T is the constant obtained, then R2 by R1 will be equal to T plus T2 small t2 divided by capital T plus small t1, where R1 and R2 are resistance of the conductor at temperature small t1 and small t2. Got the value of capital T will be 234.5 degrees centigrade for annealed copper of 100% conductivity. This completes class 1 and about the resistance and parameters, line parameters.